Chapter 7, Process Strategy. During this session, you will understand the four most common process strategies listed here. We will review process analysis tools, customer interactions in the service process, along with process design. Processes transform resources into goods and services. Since the income of the business comes from customers minus the costs, we focus on meeting customer requirements and meeting cost goals. Process strategies typically affect efficiency, flexibility, cost, and quality. The best processes are aligned with the organization's strategy. This chart maps product or service volume and variety to process type. Low volume, high variety is associated with a process focus found in projects, job shops, restaurants, and hospitals, for example. High volume, low variety works best with a product focus found in steel and glass production, commercial baked goods, and beer. A repetitive process is aligned with medium volume and medium variety found in automobile and appliance production. Finally, mass customization is a fairly new concept, and while ideal, is difficult to achieve. This process addresses high volume, high variety found in computer manufacture and some software industries. Process mapping is a great management tool to describe, manage, and optimize a process, a product, or service process. Here's an example showing the flow of materials and components going into the assembly and crating of a motorcycle. As mentioned, there are four basic process strategies. Process focus is organized around a specific process. Repetitive focus is organized as assembly lines. Mass customization supports a fast, low-cost customized order. These strategies may be implemented multiple ways, and many processes may include multiple strategies. For process focus, everything wraps around the process. Here are some of the key elements of a process focused. The high variety of products is supported by the flexibility of the process. Note the added complexity of planning and scheduling when a process focus is in place. An example of process focus will be found at the typical hospital. Medical procedures are typically customized for the patient with many different starting points with a variety of outcomes. Timing is intermittent with multiple process routings. Repetitive focus takes advantage of assembly lines to reduce cost and produce repeatability. Assemblies often consist of standard parts and sub-assemblies. Modular assembly is common. This method is less flexible than process-focused lines, but is more efficient. Harley-Davidson uses a repetitive process to build motorcycles. Inputs include raw material and module inputs. The goal is to create a limited set of standardized motorcycles that are assembled in many combinations to create many motorcycles. For a product focus, facilities are organized by product with a high volume but low variety of products. Due to the use of continuous production lines, the process is efficient with low variable cost but high fixed cost. Each production line is a major investment. Frito-Lay uses a product focus to mass produce high volume snacks in a continuous process. A limited number of inputs create a finite variety of products differentiated by mix and packaging size. Mass customization tries to create the best of both worlds, using high volume techniques while producing a unique customer experience. Often this customization is completed by using standard hardware devices with a wide variety of loaded software. Dell Computer uses mass customization to create custom computers on demand. Customers select among a list of standard parts, modules, and software loads. The result is a high volume, high variety output, producing custom PCs and notebooks. This table shows the impact of mass customization techniques, increasing the volume of customer choices for a variety of product types. Similarly, this slide compares the four process types by job instructions and inventory quantity. This slide compares the processes based on whether products are made to order or made to forecast. The scheduling model for each process focus is also considered. Finally, this slide reviews the cost model and compares fixed and variable costs for the different process types. Now that we have considered the four major process types, we look at various tools used to design your process. These tools include crossover charts, flow charts, process mapping, value stream mapping, process charts, and service blueprinting. For the crossover chart, we look at multiple options and evaluate the fixed and variable cost. The goal is to find the points where the total cost points to one option versus another as being most cost effective based on product volume. For the data given in the previous slide, we find the volume where the total cost is identical. Mathematically, we calculate the volume V1 where software A and B have the same total cost. We see that the crossover point from software A to software B is at a volume of 2,857 reports. Similarly, the crossover point comparing software B to software C is 6,666 reports. This slice graphical represents the previous data showing the three software products and their respective fixed and variable cost. The crossover points are identified where one total cost line crosses another. Thus, software A, the green line, is the most cost-effective at a volume of up to 2,857 units, while software B, the yellow line, is best for volumes from 2,857 to 6,666 units. Finally, software C, the red line, is the choice for volumes above 6,666 units. The next series of slides review tools used for process analysis and design. We will discuss the movement of material through flow diagrams or flow charts, and then stop. The next series of slides review tools used for process analysis and design. We will discuss the movement of materials through flow diagrams or flow charts, and then use time function mapping to see the progress of the process over time. This is a typical process flow diagram for the assembly of a motorcycle. We start with the first process, frame tube bending in the upper left corner. We move to the right with subsequent process steps until we create the completed motorcycle at the lower right. Note the components arrive at the assembly line on a just-in-time basis from various work cells. This highly effective flow turns 450 parts and sub-assemblies into a completed motorcycle in 3 hours. This time function process map shows the steps associated with a customer order fulfillment process as originally defined. Not only do we follow the process steps, but we see that the steps are spread out over time. The time scale is on the horizontal scale, while the vertical lists the various entities responsible for each step. Each horizontal slice holds the steps tied to the entities on the left. These are often referred to as swim lanes, since they are similar in appearance to the lanes roped off with a lap pool. For example, the warehouse is responsible for 3 different weight steps. This process map is useful for understanding cycle time along with the transportation complexity of the process. Every time the product changes swim lanes, there is an opportunity for lost communication. This new map shows the revised process map once the process has been improved. Graphically, the flow is simpler. 2 weight steps and 1 move step have been eliminated, plus the 2 value-added steps of print and extrude have been combined to a single location. The result is a reduction in the number of swim lanes crossed from 10 to 6, and a total cycle time reduction from 52 days to 6 days. Note that this is achieved without reducing the time available for the value-added processes. Quite an improvement. This process chart shows the process associated with creating a hamburger. The steps are listed to the right, with time and distance traveled for each step listed on the left. Note the 5 different process types, each with its unique symbol. The circle represents an operation and is the only value-added activity, while the others represent waste. Of the 9 operations, only 2 add value. This may represent an opportunity for improvement by eliminating non-value-added steps and shortening travel distance. Value stream mapping identifies the steps of the process that add value along the entire supply chain, from initial suppliers through the distribution process to the final customer. Value stream mapping is another method for understanding a complex process and exposing opportunities for improvement. In addition to material flows, communication links for forecasts and orders are also displayed. Note the 4 value-added processes listed near the bottom. In summary, only 140 seconds of value-added time are added over a duration of 26 days. A service blueprint is a specialized process map used to analyze a service process. The blueprint focuses on the customer and considers 3 levels of interaction. Potential failure points along with sales opportunities are identified. This service blueprint displays the processes found at Jiffy Lube. The first level represents the customer. The second, middle level depicts the interaction with the customer, while the third level displays process steps away from the customer. Using our standard mapping methodology, ovals represent process steps while diamonds represent decision points. The process moves forward from each decision point based on the decision made. The red circles represent failure points or opportunities of increased sales. For example, the first red circle in the upper left is a risk, as there may be a miscommunication between the service technician and the customer. At the same time, this is also an opportunity to upsell additional services and products. Customer interaction is critical for success. This interaction can be managed to be more effective and efficient. As noted, this is an opportunity for increased sales. This matrix maps different service organizations based on the degree of customization versus the amount of labor required. Customers requiring specialized service often require additional labor and the engagement of more highly skilled professionals. This completes our discussion on the service processes. We now consider the application of technology to manufacturing. Different levels of automation are available to enhance operations. Possibilities range from standard machine technologies and process controls to more advanced automated systems. Each has its own strengths and weaknesses and must be applied appropriately. Computer integrated manufacturing uses data to link the various steps of the process, from original engineering design through fabrication and delivery and on through financial and customer service. This technology aids in process control and flexibility. Here are some examples of computer integrated manufacturing. Note the flow of data that supports the flow of material. Accurate and timely data is key to success. Services can also leverage technology to improve process capability. Examples include financial services, education, utilities, government, restaurants, and communications companies. Again, marrying the data with automation makes these enhancements possible. Additional examples are shown here. Technology makes a difference at hotels, wholesale retail, transportation, healthcare, and airlines. How has your world been affected by these technologies? It's clear that a focus on process can improve the customer experience for both product-based and service-based activities. Efficiency is also a possible outcome. Decisions associated with equipment selection are essential. Major capital investments can result in major process improvements if properly selected. Decision factors are listed here. It is important that the process is optimized before the purchase of equipment. It makes little sense to automate a weak process. Better to simplify and optimize first. Flexibility may be a key factor in your business, especially if forecasts are difficult to define or competitive pressures may call for a quick response. Flexibility is generally expensive and difficult to achieve. I want employees to be empowered to adapt, but we have to make sure that overall quality does not suffer. Failure to adapt can result in missing a major business opportunity. When reviewing a process, we consider whether the process is aligned with our overall strategy of differentiation, response, or cost. Have non-value added steps been eliminated to maximize customer value? Will this process move our business forward by capturing customer orders? Once the previous questions have been answered, we may embark upon a redesign of our process to improve alignment with our goals. Past beliefs are reconsidered with an objective of defining the best process using current technology and data. This is often called a greenfield analysis, as if we are starting from scratch. If we had our current knowledge but could start over, what would the process look like? Once this theoretical model is defined, we identify the appropriate steps to move forward toward that ideal. This may not be possible in one step, but it provides a roadmap to the future. This roadmap should be reviewed regularly as technology and processes evolve and business realities change. The process of moving from current processes to a future state is not easy and may be expensive to deploy. Change may mean starting over or establishing a long-range plan. Either way, it is important to continuously improve your processes. If you don't, your competitors certainly will.